Okay, so thank you very much. First of all, I would like to thank the organizers for inviting me and for organizing this very important, very interesting symposium in this conference, and also for giving me a chance to talk. And it's actually a very pity to not to come to the boardroom. Due to the restriction for travel in Japan. So today I would like to talk about the spectroscopic view of Martensitic phase transition, especially in cobalt-based Heusler alloys. Okay, so first of all, let me remind you kind of variety of various functionalities which can be realized with Heusler alloys, ranging from half metallicity, for example, appearing in cobalt to manganese silicon and so on. Also, the good thermal electricity is realized for iron-based Heusler alloys. And also recently, the spin gapless semiconductor was predicted for manganese to cobalt aluminum and related alloys. And we can also see some topological aspects in several Heusler-based alloys. Recently, substantial thermal electricity and Nernst effect was found in the cobalt to manganese gallium alloy, which may be due to the some berry curvature in the band structure. And as a main topic of the symposium, nickel-based, many of the nickel-based Heusler alloys exhibit magnetic caloric and magnetic shape memory alloys, as you can see here. So one of the prototypical shape memory alloy is nickel to manganese gallium, which has been extensively studied. There was an interesting prediction 30 years ago by Professor Fujii in Kagoshima University, Japan. And there was a prediction for the structural transformation, which could be driven by the Yantila effect. As you can see, there is a sharp peak at the Fermi energy in the minority spin channel, which can be a driving force of the lattice instability. Actually, in the tetragonal phase, the calculation shows that there is a splitting at Fermi energy. Yeah, this kind of electron structure could be the underlying mechanism of the Martensitic phase transition and the Martensitic phase. So in order to maybe to look at the electronic structure directly and experimentally, it may be important to organize or develop the future, maybe future functional materials with improved functionalities. So one of the experimental tools which may be good for you is a photoelectron spectroscopy. As you can see here, irradiated by synchrotron radiation, you can just count a number of photoelectrons as a function of kinetic energy, sometimes as a function of emission angle. So you get approximately the density of states below the Fermi energy, maybe according to the energy conservation rule. But I'd like to mention that there is a serious problem, which is a short penetration depth. In other words, surface sensitivity. So using the conventional photoemission spectroscopy, using the some ultraviolet or soft X-ray radiation, the kinetic energy of a photoelectron is as small as 100 or 1,000 electron volt, which enables us to observe a very surface region. I mean, penetration depth is as small as 10 angstrom, something like that. So in order to get a true bulk electronic structure, you need to use higher photon energy. You need to use, let's say, hard X-ray. So on the other hand, cross-section of photoelectrons decreases very much with increasing the kinetic photon energy. That means it is very difficult. It is almost impossible to do hard X-ray photon emission using the conventional X-ray source, which is typically used for the X-ray diffractions. Therefore, we have to choose the brilliant synchrotron radiation, which can be provided by a large facility like Spring 8, shown here. Okay, so here's an example, which was reported several years ago in collaboration with Professor Vladimir Ternenko and Professor Barandiaran in the Basque Country University. We worked for the off-stoichiometric nickel-2 manganese gallium. We chose two typical samples. One shows a higher Martensitic phase transition temperature where the cubic phase is much stabilized. The other one shows a much lower Martensitic phase transition temperature. So you can change this temperature by changing the stoichiometry. As you can see, the much higher density of state at the Fermi energy is observed for the sample with a higher Martensitic phase transition temperature. And of course, the other sample with a lower Martensitic phase transition temperature shows a smaller density of states. This result tells us that when you have a Fermi energy just near the peak of the density of states, actually this is in the minority spin channel, you can realize that stabilize the cubic phase. No, I'm sorry. This you can just stabilize. I mean, you can cause the instability of the cubic phase because a large energy gain can be expected when you have a Fermi energy near the peak of the density of states. On the other hand, when you have some Fermi energy just at the tail of this density of states, maybe you can say that actually this is large energy gain is not so much obtained. This kind of thing, I mean, this result tells us that Fermi energy position is also very important. So now we would like to compare the calculated density of state for nickel-2 manganese gallium and cobalt-2 manganese silicon, which are actually extensively studied. So as you see, as I said, the very sharp peak is located near the Fermi energy in the minority spin channel like this. It can be a driving force of the lattice instability, which may be important for the Martensitic phase transition. On the other hand, in the cobalt-based alloys, which typically shows a half metallic band structure, you have a large minority spin gap here. So these results may indicate that it may be quite difficult to integrate both shape memory and half metallicity in a single compound, for example. So first, I'd like to remind, I'd like to show you the little old work which was done by us and Professor Chernenko's group for nickel iron gallium films deposited on magnesium oxide substrate. The film sample is very, very important for application. So actually we have worked with hard X-ray photon emission and X-ray magnetic circular dichroism for this alloy in order to get insight into the underlying mechanism of this phase transition. As you can see, the Martensitic phase transition occurs near 200 Kelvin, as you can see here. Here's a photon emission spectra as a function of temperature ranging from 300 Kelvin down to 50 Kelvin. And the horizontal axis here is the binding energy with respect to the Fermi energy. Fermi energy is located at 0. And the vertical axis is it is exactly the number of photoelectrons, intensity of photoelectron. So overall density of states are identical for all the temperatures, as you can see. but some changes are seen just near the Fermi energy. So here's a magnified picture of the density of state near the Fermi energy. So you can see the steep reduction on cooling of photoelectron intensity, as you can see in the blue curve. And you even observe the shoot gap upon the Martensitic phase transition. So this kind of experimental result suggests that band Yantila effect may be responsible for the Martensitic phase transition. So here's the result of the X-ray magnetic circular dichroism experiment in order to get the element-specific magnetic moment. You can just tune the photon energy to get some magnetic moment on the specific element. For example, you see the iron to be 3D edge, you see the negative peak here and the positive peak here. And for cobalt and nickel sites, you see also similar behavior, but with a different amplitude of dichroism. So we know now that with this result was the same sign of the dichroism. We see the old iron 3D and cobalt 3D and nickel 3D moments aligned parallel. But we have some difference among these three elements. We see a big enhancement of nickel moment at low temperature as compared to the other elements. We see some 3 times higher magnetic moment at 50 Kelvin compared to that at 300 Kelvin, which is moderate, 1.5 or 1.2 for iron and cobalt. This suggests that nickel 3D electronic state is quite responsible for the Martensitic phase transition. So actually, first principle calculation also shows that there is a substantial density of states, not only from the nickel 3D state, but also from the iron 3D state. But actually, the calculation shows that the enhancement of the magnetic moment is remarkable only at nickel site, which is very consistent with our experimental result. As you can see here. So, and from the X-ray magnetic circular diagram, you can also get the information of the density of states near the Fermi energy, which might be responsible for the phase transition. So now I mainly want to talk about the Reentrant type shape memory alloy, which is shown by the cobalt-based Heusel alloys. This actually shows the cooling-induced shape memory effect, which was reported also several years ago by Professor Kainuma's group. You see a Martensitic phase transition from high temperature to low temperature. This is actually the same as a nickel-based compounds. But you see again the transition to the cubic phase at lower temperature. Then I would like to say this transition is Reentrant type transition. So we had 2 kinds of samples, cobalt 51.7 and cobalt 15.8, different stoichiometry. So upper one, the cobalt-rich sample shows the Reentrant Martensitic phase transition temperature at rather lower temperature. So on the other hand, cobalt-poor sample shows a higher transition temperature. We compared these 2 samples. So here you see the X-ray magnetic circular dichroism spectra at cobalt and chromium edges for cobalt-rich sample. As you can see, both elements, cobalt and chromium edges, you see the same sign. You see the identical signs. And again, this indicates a parallel magnetic moment between cobalt 3D and chromium 3D spin magnetic moments. And also in XMCD intensities, it grows very rapidly with decreasing temperature. So this is also similar to what we observed for nickel, iron, cobalt shape memory alloy films. However, in this case, both elements shows a similar behavior. This indicates that both of the cobalt and chromium 3D local dose both possibly be responsible for the reentrant martensitic phase transition. So now we see some valence band photoemission spectra. On the left-hand side, the spectra. On the left-hand side, I'd like to show you the change of the density of states, just starting from the 300 Kelvin down to 20 Kelvin. You see almost similar behaviors for all the temperatures, except for the something very close to the Fermi energy. In warming, you see also the change in the density of state near the Fermi energy, but there is a subtle difference between cooling process and warming process, which I will talk about later. So first of all, I'd like to show you the prominent peak is existing at the binding energy of 6 eV and 8 eV. I take this. The other sharp peak, this is actually the core level spectrum from the gallium 3D photoelectrons. So we use this core level in order to normalize the valence band spectra at various temperatures. So I'd like to show you the valence band spectrum in cooling process precisely, and then you see some broad feature near the Fermi energy at room temperature. By decreasing temperature, you see some changes, especially from 150 Kelvin. So you see the growth of the deep at binding energy of 0.75 eV. Accordingly, you see the appearance of the peak at the Fermi energy. And we actually took the difference between the spectrum of at the certain temperature from the spectrum at 300 Kelvin. Then you see the deep corresponds to the positive peak in the different spectrum. So as you can see, so the deep grows from 150 Kelvin and down to 20 Kelvin. And you also see negative peak here. This corresponds to the appearance of the sharp peak near the Fermi energy. In the warming process, you again see the similar change, but as you can realize that at 200 Kelvin, warming in the warming process, you still see the dip at the 0.75 eV, while this dip at this positive peak is absent at the same temperature in the cooling process. This reminds us of some hysteresis behavior of this change in the density of states. Actually, this change is scales exactly with magnetization curve, so that indicates this density of state change is due to the some Martensitic phase transition. So I believe that electronic state near the Fermi energy is again responsible for the reentrant Martensitic phase transition. So now let me show you the first principles calculation, density of state, theoretical density of state in the cubic phase and also in the tetragonal phase. As you can see, in the cubic phase, you see the minority spin gap, which shows a half metallic band structure. In the tetragonal phase, you see that this half metallic gap in the minority spin gap is collapsed. Anyway, for both phases, cubic phase and tetragonal phases, the cobalt 3D is drawn by the orange color, and the chromium 3D DOS is represented by the green color. So you see some both contribution from cobalt 3D and chromium 3D states near the Fermi energy. And this is actually consistent with the experimental result of the XMCD. You see the similar enhancement of the cobalt and the chromium 3D magnetic moment. Okay, so and here's a total energy, calculated total energy as a function of C over A. So in the cubic phase, C over A is 1. You see half metallic gap again. And this half metallic gap, minority spin gap, is made mainly by cobalt EG states. And when you increase the C over A ratio, the half metallic gap is a little smaller now. So at 1.12, you see there is a sharp peak in the minority spin gap. So that means the half metallic gap is collapsed already. So in the local minimum at C over A is 1.3. You see there's some flattened density of state in the minority spin channel. So now I would like to compare the experimental valence band spectrum with the theoretical density of states, which was corrected by considering the cross-section of each orbital contributing to the DOS. So we see some good correspondence of this appearance of the peak in the experimental spectrum at low temperature with the calculated dose, which shows a sharp peak here. Also, there is also dip in the theoretical density of states. This is totally consistent with the experimental result. And we now know that this sharp peak near the Fermi energy is mainly contributed by cobalt 3D and 4s orbitals. And the disappearance of the dip and peak is also reproduced in the calculation in the tetragonal phase. So now we again compare the result between theory and experiment. So we see again the difference between the 300 Kelvin and 20 Kelvin density of states. You see the negative difference near the Fermi energy and the positive difference just at 0.7 eV. This behavior is overall reproduced by the calculation, but you have a little difference near the Fermi energy. In the calculation, you have a positive peak here. This suggests that there is some difference in the Fermi energy position between the calculation and experiment. When you move the Fermi energy in the calculation to the higher binding energy a little bit, the theoretical band structure reproduces very much the experimental result. Yeah, anyway, the spectrum near the Fermi energy mainly reflect the change of cobalt 3D orbitals. And also positive differences also reproduced by the calculation as I mentioned. And the Fermi energy position is lowered in the experiment due to off stoichiometry. Actually, the calculation was made for the stoichiometric samples, while the experiment was done for these off stoichiometric samples. So now we compare the difference of the cobalt concentrations. As I mentioned that cobalt 4 sample has a higher transition temperature compared to the cobalt-rich samples. And from the core level photo emission, you see some core level shift by 70 millieV. Cobalt-rich sample has a lower binding energy peak, while the cobalt-poor sample has a higher binding energy peak. This suggests that the Fermi energy position for the cobalt-poor sample is higher than that of the cobalt-rich samples. And by the way, we actually always check the state of magnetization of the sample by just attaching the permanent magnet. As you can see, the cobalt-poor sample is magnetized. I mean, attach the permanent magnet, as you see, because it is ferromagnetic. And while the cobalt-rich sample does not attach the magnet, which means it is already in the martensitic phase at room temperature. So as you can see, the density of state is much different in terms of the appearance of peak and appearance of the dip in the cubic phase. This cobalt-poor sample is in the cubic phase, as you can see. So, and so I mean, the prominent peak near the Fermi energy at 300 Kelvin for cobalt-poor sample is similar to that for the cobalt-rich sample at low temperature. So now I would like to, I'm going to summarize our discussion. Now we compared the cobalt-rich and the cobalt-poor samples. Now we know that Fermi energy position is higher for cobalt-poor sample. And the cobalt-rich sample has a Fermi energy position near the peak of the density of state near in the majority spin channel. By the way, stoichiometric composition locates the Fermi energy near this density of states, not far from the peak of the density of states in the majority spin channel. Which means off stoichiometry maybe drives the lattice instability. Actually, cobalt-rich sample maybe has the closest Fermi energy, closest to the peak of the density of states, which may be the reason for why you have a lattice instability. But at low temperature, the magnetic moment is actually developed. That helps to get the half metallic band structure, as you can see here. This may be the reason why the reentrant martensitic phase transition occurs for this sample. Actually, there is a competition between the half metallic band structure and lattice instability due to the large peak, large density of state at the Fermi energy. Probably that may be the reason why you have a cooling-induced martensitic phase transition down to the cubic phase. So let me summarize my talk. So we have studied the cooling-induced shape memory effect in terms of the electronic structure for cobalt-2 chromium-gallium silicon systems. This shows a reentrant martensitic transformation at low temperature using photoemission and X-ray magnetic circular dichroism experiments. So we have observed a high density of state made of cobalt-3D and chromium-3D orbitals, which may cause a lattice instability and stabilize the martensitic phase. Actually, cobalt-rich concentration leads to the hole doping and the lattice instability at the ferromagnetic parent phase. So finally, we discussed the competition between the band-Yantla effect and the half metallic band structure. Probably developed the magnetic moment at low temperature stabilizes, maybe stabilizes the cubic phase, cubic ferromagnetic phase through magnetic exchange interaction by opening the half metallic gap. Okay, so finally, I would like to introduce our collaborators. This work was mainly done by the Dr. Kazuki Sumida, now in JAEA. He's a former student in our lab. And this work was done in collaboration with Professor Kainuma and Professor Umetsu. And first half of the work was performed in collaboration, in strong collaboration with Professor Vladimir Chernenko and Professor Barandiaran in the Basque Country University. And the experiment was done at Spring 8, where the Professor Dr. Ueda is in charge. And also theoretical calculation was made by Professor Shirai and Professor Miura. And finally, I would like to thank Professor Kanomata for the entire collaboration of this work. Thank you very much for your attention.
Do you have an idea why the Martensitic transition is so spread in temperature? Because according to the data you showed from the density of states that correlate very well with the magnetization data, the Martensitic transition spread from, let's say, around 150 Kelvin down to 20 Kelvin. So it's a very broad temperature range. Do you have an idea why it's so spread in temperature? Yeah, exactly. Yeah.
Yeah. Actually, even at the low temperature, you have both paired cubic phase and multicubic phase. Actually, there is a mixture of the two phases, according to the paper published in 2013. So actually, I don't have an answer, but the situation is like this. Then maybe parent phase is not completely dominant in the low temperature, as you can see here. So it seems that gradually Martensitic phase grows with increasing temperature. Actually, I would like to ask about, I would like to give you a same question in principle, but I'm sorry, I have no answer.